So there's one applied homework problem, application problem, where I suspect there will be questions. So I want to anticipate them a little bit. And I think there will still be questions, but some comments might help. So here you've got an LC circuit. And that's going to give you, if I just say an LC circuit and all you've got is an inductor and a capacitor, then that's going to end up giving you some homogeneous second order linear differential equation with constant coefficients. But once I throw in this battery, where there's this time dependent voltage, there's this voltage changing in time in series with everything else in the circuit, that's going to make the differential equation be non-homogeneous. Okay, so once you set up your differential equation, which is just going to be a matter of using this, the equation for RLC circuits that's derived on page 52, you just don't have a resistor in there, so you have R equals 0. But it's basically just this. Once you set that up, you'll have to apply our methods to try to find out. You've got some initial conditions here. So to satisfy the initial conditions, you will need, looking at this, I just realized it's actually interested in the charge on the capacitor, not the current in the circuit. So probably you will not want this. You will want the version of this that is about charge. So I think it has Q, 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 and then no prime here. But you can find that in the book. Anyway. You've got some initial conditions, so that means you will have to find a general solution to a non-homogeneous differential equation. So how will you do that? You will apply this method here, where you find a particular solution to the non-homogeneous, general solution to the homogeneous, add them, then you've got these two free parameters, C1 and C2, and you've got your initial conditions. At t equals 0, Q is 0, and I, which is the derivative of Q, is 0. So you will have to impose those initial conditions, and you'll get values for C1 and C2. It's not going to be 0, 0, probably. Then this is the question I wanted to comment on. What is the steady state behavior of the circuit? So often with these kinds of circuits, with also with the damped harmonic oscillators, if they're also forced damped harmonic oscillators, often you'll get two kinds of terms in your solution in the end. So you'll get some parts that decay in time. As t goes to infinity, they die off. So parts that might be multiplied by an exponentially decaying factor. That's what you'll see in this setup. And there are other parts that do not die off. They stay there, so that even after you run time for a long time, those terms in your solution still contribute. So very often, let me give you a crude drawing of what I'm thinking of. Like if this is time, and this is your solution, charge on the capacitor plates or whatever, you'll have some like weird kind of, it has to be a function, but you'll have some kind of weird behavior initially, and then it becomes more regular later on, and you get some long-term behavior. This is coming from the fact that you have some like funky terms in your answer. X of t equals some terms, but all multiplied by maybe stuff that decays, like e to the minus 7t or something. And then you've got some other terms. And these terms are maybe what you have as something regular, and these terms added to these terms when this portion is significant, so this part has not decayed so much, contribute to the funky behavior at the beginning. This funky part at the beginning is called the transient part of the solution. And these terms are this is the transient term in the solution. Transient means like temporary, it'll pass. Eventually it settles into a rhythm, and this is called the steady state part of the solution. So in this problem, when you get your final solution, figure out what's the part that's going to decay as time goes to infinity, and drop that part and then only give the other part. That will be the steady state behavior. Often this is what people are interested in. They want to know, because often exponential decay is very fast. So what actually happens when you activate the circuit or whatever the system is, what's actually going to happen is all the weird stuff is just going to happen at the beginning, and then the steady state stuff is what you're going to keep seeing. So this might be a very short time period that you see all this complicated stuff.